Let's start here. Okay, we're going to look at computer organization and architecture here. Now, a very intelligent man called von Neumann was involved in computer organization and architecture, just in case you think it's a very boring subject, but it isn't. And he was at Princeton alongside Einstein, and here is a photo of very eminent Princeton professors. And you know, there are articles around von Neumann versus Einstein on who is cleverer and smarter. So the objectives are to see 1. How buses are used to pass data and instructions. 2. Different types of memories, RAM and ROM. 3. Concept of addressable memory. 4. How external devices are handled. 5. The difference between the von Neumann and Harvard architecture. 6. We'll allude to past paper questions as well. Okay, none of this will mean anything to you. Hopefully you'll have a little bit of idea at the end of this session, but you may not. These objectives are a bit like a disclaimer to say that I've told you what you need to learn. Now you pay attention, rather like a financial disclaimer. I absolve all responsibility. Right, internal and external components. What's an external component? Well, examples include input-output devices like VDU and keyboards. Internal components, they're within the central processing unit, such as the processor, main memory, input-output controllers, system bus, of which there are 3 types, address bus, control bus, data bus. We will concern ourselves today with internal components, and basically it's the internal components which are doing the work, carrying out the computation, and these internal components, they work together and they are connected together. So you have like the processor and the main memory, and there are communication channels of buses through them. Okay, let's first of all look at what a processor is. Processor responds to and processes instructions which drive the computer. It comprises of the control unit, and control unit, within the control unit there's the executes a fetch, decode, execute cycle. If you don't know what that is, look it up. The arithmetic logic unit, or ALU, performs operations on the data, and it makes use of registers. Registers are special memory cells that operate at high speed. All arithmetic and logical operators are placed within registers. The processor communicates with the main memory, and the main memory is used to store data and instructions. So it is a store of data and instructions. It is connected to the processor, and what the processor does, it fetches the data and instructions stored from the memory and processes them and carries out computation. Now there are 2 main types of memory, RAM and ROM. RAM is random access memory, ROM is read-only memory. Favorite exam questions are, what are the differences between the 2? So random access memory, it's temporary memory, which can be accessed very quickly. It is volatile. RAM is volatile, which means if you turn the computer off, all of the contents of RAM are lost. And when you run a program on your computer, the entire program or parts of it are loaded onto RAM. So, for example, you know, like word processors and spreadsheets, the more memory you have, the more applications can be loaded at any one time. If you're creating a formula, they are stored temporarily in RAM. And when you turn your computer off, it closes down, say, your spreadsheet, and your worksheet will be lost. What is ROM? ROM is a method of storing data and instructions. ROM is non-volatile. Unlike RAM, which is volatile, ROM is non-volatile, which means the contents are not lost when you turn the computer off. We have something called programmable RAM, but we shall not concern ourselves with that here. What we will look at today is traditional ROM, and here the ROM is used to store a limited number of instructions which relate to the setup of a computer. The settings are stored in BIOS. BIOS stands for Basic Input Output System. When you switch your computer on, it carries out a number of instructions. For example, it checks the hardware devices that are plugged in. It loads parts of the operating system, and all of these instructions are stored in ROM. These instructions are programmed in ROM by the manufacturer of the PC. There is this concept of addressable memory. All memory is addressable. RAM, ROM, etc. is addressable, which means memory is what it means is that the memory is made up of millions of cells which store data and instructions, and each cell has an address by which it can be uniquely identified. So each memory cell has a unique address. Now, memory is organized in a systematic way, and the addresses are different programs are stored in different parts of the memory. Blocks are allocated for different things, like blocks are allocated for operating system, utility programs, library programs, application programs. If you do not know what they are, you look them up. And a memory map shows which programs are stored in which addresses. These are arbitrary addresses. You note that the memory addresses are shown in hexadecimal format rather than binary. They are stored in binary, by the way, but they're shown in hexadecimal because hexadecimal is shorter and it's easier for humans to read. Right, so we talked about the processor within the CPU, and we talked about the memory. And obviously there's communication which goes on between them in order to carry out computations. And these buses are like channels of communication here. And so here you have what you call the three types of buses: data bus, address bus, control bus. Here you have the data bus. Note that the data bus between the processor and the memory is bidirectional, and it's carrying data and instructions. You have the address bus here, and the address bus note is what? Unidirectional, and it's used to specify a physical address in memory so that the data bus can access it and know where the data and instructions are stored. Now, what is this control bus here? Well, the control bus it controls the sort of, all this system. There's a lot of data flowing around, and the control bus controls the sort of flow of data around the processor, between the processor and the memory, and between the processor and input-output controllers. We have not mentioned input-output controllers yet, but we will just mention them here for sake of completeness. And so, the job of the control bus is to ensure that correct data is traveling to the right place at the right time, and it involves synchronization of signals and the control of access to the data buses and the address buses, which are shared by a number of devices, as we will see later. And the control bus also transmits pulses which are being delivered by the system's clock. Another representation of, say, the bus structure. Here we have, you could see this representation in an exam. I would strongly advise you memorize it and you can draw it out. Note that the control bus is bidirectional like this. The data bus is bidirectional like this. Bidirectional arrows here from the data bus to the processor. Two bidirectional arrows here from the control bus to the processor and the memory. This address bus is the odd one out. It's unidirectional. Data is passing from the processor to the address bus. Data is passing from the address bus to the memory. Memorize. Okay, now we've talked about the data bus. Now, obviously, the data bus is carrying data. There's a certain amount of data that the data bus can carry. So what are the factors which sort of affect the performance of the data bus? Well, data bus, it's dependent on how many wires on the bus. So an 8-bit data bus has 8 wires. So each wire can carry a 0 or a 1. So an 8-bit data bus can carry 2 to the 8, 256 combinations. How many combinations can a 16-wire data bus carry? Will it be 2 to the 16? So the greater, obviously, the width of the data bus in terms of wires, the more data it can carry or be transmitted on it in one pulse of the clock. So the size of the data bus, you're talking about the number of wires, the width, is a key factor in determining the overall speed and performance. Now, the data bus width is also known as word length of the processor. So the word length, you can think of the number of bits that can be addressed, transferred, or manipulated as one unit. Also associated, sort of, the address bus also has size associated with it. The size is measured in bits, and it represents the amount of memory which is addressable. So an 8-bit bus gives rise to 256 addressable memory cells. This means a program can contain a maximum of 256 separate instructions or data items. A 32-bit address bus is common for most PCs, and this would provide 4 gigabytes of addressable memories. A 64 address bus would okay, let's stop that now. Now, what else do we have here? Okay, now remember this diagram here, and there's a bit in the middle which is empty, and now we have filled in this bit in the middle, populated it with input-output devices, or sort of keyboard input controller, VDU output controller, disk output controller. What do we mean by that? So it's a controller which looks at the keyboard, a controller which looks at the VDU, a controller which looks at the disks. So what do we mean by that? Now the processor is connected to the memory and communicates via buses. The processor also sends and receives signals to various input and output devices, but it doesn't send the signals directly. It sends the signals through an interface called an input-output controller, and that's what these are, sort of interface of input-output controller. Each device has its own controller, which allow devices to be connected to the processor at any one time. So typically, a computer will either have a monitor controller, a mouse controller, a keyboard controller, and a hard disk controller. And the features of the input-output controller, it translates signals into a format required by the processor. Now, there are lots of types of devices, many different types. There are many different types of processors, and the input-output controllers provide the flexibility to add new devices without having to redesign the processor. In addition, the input-output device controller is used to send buffer data sent between the processor and the device, so the processor does not have to wait for the individual device to respond. Remember, input-output devices respond relatively slowly compared to the speed at which the processor can work, so you need some sort of buffering system. Now, I advise you to memorize this diagram off by heart, draw it. So quite often you're given this diagram in an exam with bits and pieces missing, and you're asked to identify the missing bits and pieces. Extra to this diagram, previous to the other one, is the keyboard input controller, VDU output controller, disk input output controller. Note, as usual, note the direction of these arrows here. So keyboard input controller, unidirectional arrow here, unidirectional arrow here, bidirectional arrow with regards to the control bus. Actually, the control bus has bidirectional arrows to everything, but the data bus sometimes has unidirectional arrows, and it has a unidirectional arrow to the VDU output controller going from data bus to VDU output controller, and a unidirectional going from keyboard input controller to data bus. The address bus here is unidirectional, and here the arrows, the data is going from address bus to keyboard input controller, address bus to VDU output controller, address bus to disk input output controller, address bus to memory controller. Memorize, know how to draw. You will probably be asked it in an exam. Okay, there is a question on this, June 2016, Comp 2, number 4. You're given something like this with bits and pieces missing, as I said, and you're asked to fill it in. Von Neumann architecture. Remember von Neumann? You mentioned him at the beginning. Okay, what's von Neumann architecture? Von Neumann architecture. He proposed that instructions and data are stored in the same memory, and they both pass through the same bus, the data bus, in and out of memory. A very popular architecture. Here we have the Harvard architecture, and in the Harvard architecture, there are two different memories for the data and the instruction, and they pass through different buses, and the different buses address the different memories. So obviously, if I put them up side by side here, obviously the advantage of the Harvard architecture is that instructions and data are handled more quickly, as they do not have to share the same bus. A program running on Harvard architecture can be executed faster and more efficiently. Harvard architecture is widely found in embedded systems such as mobile phones, burglar alarms, where there is a specific use rather than on general purpose PCs where you would find Neumann architecture. Harvard architecture's also got extensive application in audio and video processing products, and in practically every audio and video processing instrument you will notice the presence of Harvard architecture. Harvard architecture also makes use of DSP, digital signal processing, which makes continuous real-world data such as audio or video and compresses it to enable faster processing. Chips are optimized for DSP, tend to have much lower power requirements, making them ideal for applications such as mobile phones where power consumption is critical. So this question came up for a couple of marks. June's 2017, Com2 number 1. Explain why Harvard architecture is sometimes used in preference to von Neumann architecture. Well, I think we have just sort of explained that. It's Harvard, programs can be executed faster and more efficiently, and so on and so forth. Okay, I think we've reached the end here, and I hope you found it somewhat useful. You need to obviously do far more research, but hopefully this has started you off.